This is a review for a quiz covering sections 2.1 through 2.4. The first thing we did in 2.1 was identify patterns, such as adding 2 repeatedly to get our next number, or skipping every other day and recognize that the next day is Sunday, or multiplying by 2 and then by 3 and then by 4 and recognizing the next number we'll find by multiplying by 5. This process is called inductive reasoning. Based on an observation, or a series of observations, we make a guess about what comes next. This guess is called our conjecture. The next idea was when we had a conjecture, such as the product of an even number and odd number is odd, we can figure out if this is true or false, and one way to do that is to look for a counterexample. So a counterexample is a single instance where, if we follow the rules of the conjecture, our answer is not true. Here, if we take an even and an odd number and find their product, it's even, not odd. Then we looked at conditional statements, these if-then statements, where we have a hypothesis leading to a conclusion. It's not always left to right, though. Notice these are equivalent statements. If he is sad is the hypothesis in the second one, and John eats ice cream is our conclusion. So the order might be switched around. Watch closely for that if. Then we practiced a variety of logical statements. Given a conditional statement, starting with a hypothesis leading to a conclusion, we either move things around, switching them, or negate them to come up with the converse, inverse, and contrapositive according to this pattern. So consider an example conditional statement. If a shape is a square, then it is a rectangle, which is true. The converse would be to flip these around and say, if a rectangle, then a square, which is not true. So we would say that converse is false. The inverse would be say, if not the original hypothesis, then not the original conclusion, which is also false. And the contrapositive says, if not the original conclusion, then not the original hypothesis, which in this case is true. And actually this pattern of having a true conditional statement and a true contrapositive with the converse and inverse being false is called logically equivalent statements. An example of a biconditional statement: if an angle is 90 degrees, then it is right. That's our conditional statement, and we take the converse by switching these around and say, if an angle is right, then it is 90 degrees. If both of these are true, then that's considered a biconditional statement, and we can write it like this: an angle is 90 degrees if and only if it is a right angle. And one way to shorten that if and only if is to write an if with two f's. Notice we don't have an if and a then in these biconditional statements. We next distinguished between inductive and deductive reasoning. Inductive reasoning is a guess based on observations, where deductive reasoning involves forming a conclusion based on rules or facts, sometimes a series of them, and putting them all together. For the law of detachment, it seems pretty straightforward, but if P then Q is true, and we know that P is true, then Q is true. If our hypothesis is true, then our conclusion has to be true. This is how you form a valid conclusion using the law of detachment. If we try to reverse things and say that our conclusion is true, then our hypothesis may or may not be true. If we tried to say that it was for sure, that's an invalid conclusion. So here's an example of detachment. If ink is blue, then it is permanent. Say we are given that as a fact. And then we are told that the ink is blue. Concluding that this ink is permanent is a valid conclusion. However, given the same if-then, and then we're told the conclusion is true, that the ink is permanent, concluding that it is blue is not a valid conclusion because it may or may not be. The law of syllogism says that if A leads to B and B leads to C, then we can skip those intermediate steps and jump from A to C. So here's an example of syllogism. If we have a series of statements, such as if x equals 2 and y equals 3, and notice the repetition, and if y equals 3, then z equals 4. If z equals 4, then you fail math. We can cross off all these parts that repeat and just take our first hypothesis and our last conclusion. And we can say that if x equals 2, then you fail math.